I am Doug Leonardi. I am the president of Leonardi's Workshop, as we call it, but also the developer of a system that we came up with a few years back, specifically called the LifeSpan system, as you're seeing here. LifeSpan Building Systems was started originally, we're a private company working with WPI, but we were originally created to improve the built environment after 9/11. I don't want to get morose, but the fact is, after 9/11, everybody started looking at the political and the military and the economic aspects, and I looked at the mechanical engineering and wanted to know how to make sure that never happened again. So it wasn't to me about anything other than making sure that no matter what hit any building, that building should never itself be a danger. So first of all, it was founded with the idea of improving the safety of buildings, then the livability of the buildings. And then once we started to do that, we realized that improved the sustainability of the buildings much more than we expected. In fact, much more than some of the other products out there designed specifically for sustainability. Who we are right now, and this is important to the conversation, we are system tested, but not certified for use in industry because we haven't gone through all the factory mutual testing. We have done our lab testing, and we have proven the fact, and we've done all of our analyses, and every professor and engineer involved in this knows that it's going to work. We just have to get factory mutual certification before anything can be built right now. So what we're looking for really now is feedback for partners, or not even so much partners, but people in the industry who can help us make sure that this is what you need and what is needed, and we're not under or overthinking something that's as critical as our built environment. Okay. The problem, as we saw it 20 years ago now, almost, or 19 and a half, was that when buildings collapse, the problem, as they said in USGS report, is it's not the shaking or the event, but it's the buildings themselves that actually do damage. And when we looked at that more closely, we found that it was the concrete floors themselves, because they not only represented the largest potential energy within the structure, the largest weight waiting to fall, but they added the least value to the structure itself. They weren't actually holding anything up. They were just being used as horizontal membranes, lateral bridges between the steel structure or the column structures within the building. They were the root cause of most failures. And even though we had multiple ways in which it could fail, it usually was the weight that was doing it. And they also maximized the severity of the failure. And they are the reason why most injuries and deaths occur, and they are the one, and it is the floors and the concrete that endanger the first responders when they show up to a building. They also create dust and waste when they collapse, and there are carbon emissions just from the construction of them. So, not to mention costs. So when we looked at the buildings, we realized that the real problem in the way buildings are built today was in the concrete floors. They cause progressive collapse, which is infrequent, but it is immensely severe and complete. Destroys the whole building, everybody in it, in a matter of seconds, usually, before anybody even knows the building is failing. And it's always the fault of the floors, because you don't have enough weight to initiate progressive failure other than with those concrete floors. Catastrophic failure comes from a lot of different places, but invariably it really comes from the weight of the concrete floors driving down. Now, in the last 20 years, we've gotten better at making sure they don't fall down as much, but when they do, they still kill just as many people. And in the end, boiling it all down, we figured out that the floors are really the weak point of the design of modern buildings, that essentially we have improved every aspect of our buildings over the last 100 years, except we're still making the floors out of stone. As Daniel Levitt said, we need to make sure that when these things happen, they don't kill everybody. We can't make a building that will not fall down at all. We can only make one that doesn't kill everyone when it does, because eventually everything's going to fall down. They're all just weights being suspended in the air. Less weight, less chance of it falling. So our solution was to replace the concrete floors completely. That removes the potential energy of it. It removes the potential for progressive collapse entirely, because no floor has enough weight to trigger the collapse of the floor below it, which triggers the collapse of the floor below that. And that's really progressive collapse. And we had to make sure whatever we replaced it with was just as strong, but lighter and just as rigid, because it has to still do everything that the concrete floor did. It just has to do it lighter and more flexibly. And it has to be at least cost competitive with the existing solution, which is basic concrete. I'm actually getting a lot of wind out there. I might get a tornado, we'll see. In any case, what we came up with after a couple of years of looking at this was a system we called the LifeSpan system. What used to be called Safety Span, which is why there was some naming confusion before, but it's currently called the LifeSpan system because it's actually much more than just safety. The system as a whole is much stronger, safer, and lighter than any concrete floors in existing buildings today. Easier to put in than existing concrete and actually cheaper than concrete. And then when we looked at the whole thing, as I said, was immensely greener as well. Far more sustainable than any of the concrete buildings being put up today by sometimes an order of magnitude, sometimes as 10th the concrete carbon emissions coming out of that building. In any case, we'll get to that in detail. Please, by the way, I'd like to have a conversation. So if anybody here is either concerned or has questions or confused, please speak up. Our key here was to make sure that whatever building we make is going to be strong and safe. So we came up with a cage in place of a concrete slab. That cage had to have a rigid geometry, but also a shock durability. So it can absorb some level of shock. There's the ability to dissipate energy into the frame, but also have enough rigidity to be able to keep the building straight the way concrete would as a rigid membrane. Load redundancy, so that if any part fails, there's always other parts to pick up. So we have a three-dimensional geodesic lattice that is ideally geometrically designed to make loads redundant, dissipate them across the entire frame, and minimize the load on any given component. Because it's a regular geometry, you can infill to an existing building and you don't have to worry about cutting around edges and worrying about where you're going to pour concrete. We just have a standardized geometry we're going to put in there with any size frame wherever we want it to go. It's easy to design because of that, because it's a homogeneous geometric frame and any CAD can figure that out. And then we have lightweight components so that the whole thing becomes so much lighter than existing space frames that it becomes essentially a fabric stretched across the frames inside of the building. We're maximizing Buckminster Fuller's geodesic geometry here. Essentially the same geometry that goes into making a geodesic dome, except instead of being a dome, it's a flat surface. We take that, we make three functional layers. The structural layer that goes between the girders of the building and actually carries the load. The architectural layer that goes on the surface so that you have walking surfaces and ceiling tiles. And then there's the fire protection layer in between the two that actually protects the entire frame and the floors above and below from fire. So there you have all the three functional aspects of concrete. You have a subfloor that can hold all kinds of loads, handle any kind of shock, and protect you from fire for up to 4 hours between layers. We make the frame itself out of durable components so that each one is factory made to specific standards. They're simple. There's only 4 of them for the frame. They're lightweight, they're high strength, they're resilient to shock, and they can configure to any project. So we don't actually have to worry about whether we specify something perfectly in the CAD and the CAD stages. We can just ship a whole bunch of these things and assemble them and then adjust them as needed to be able to make the frame space we need. So then we isolated the components and we looked at them individually and we said, all right, well, we have the frames, the joints, the mount points. That's pretty much the whole frame. There's a couple of extra ones in there for adjustments, but there's really only 3 of them. So they can be perfectly designed and standardized. Then we have insulation and isolation. We're going to isolate noise. We're going to isolate vibration within the building through these panels. And we're also going to use fire panels to protect us from fire. Each panel can stop up to 4 hours. So if we have 2 layers, you've actually got 8 hours of fire protection in your building. And then there's the envelope we put on the floor panels, which are actually like a Trex-like material that is durable and paintable, and you can put screws and nails into it or lay carpet on top of it or wood paneling or whatever you want. And then there's ceiling tiles underneath. So even something as simple as the ceiling tiles, let me jump ahead here for a moment. Even something as simple as the ceiling tiles, we engineered to be as perfect as we could. So we got a lightweight panel that is also acoustic damping like any fire panel should be, and it's fire rated. And then it's got we can have other ones that have openings in them for sprinkler heads. So they're just standardized for you to pop them in and have a sprinkler head attachment right where you need them to be. No extra machining from another company to do that. You can put recessed LED lighting into them, or HVAC ducts, or utility access ways, or and most of all these components are as durable as they can be, so they can wear and tear. You can take them down as a facility owner. You can swap them out for a new color or replace them when they get worn. Every one of the components has been engineered this way. We went through all the different levels. There's about a dozen components to the system. So now what you have, instead of a process for building floors like pouring concrete, what you have is a product line of a dozen or so components. And the frame ones have been engineered to make sure that they only go together the right way, and they're color coded, and they lock together so that you know that your building is secure. But they can be removed if you use a very special tool and you twist it the right way, unlock them and pull them apart so that you can take them apart again after the fact. Everything in here has been engineered so that your facilities people can run the building long after you're gone with the components that we have, without having to have special things custom made for them. All this means that you have a much easier design phase and construction phase, and that is really appealing to to builders and developers and architects, because it simplifies every step in the process. And when you simplify the process, you make it cheaper for them. So when we talk about cost in this, really I'm talking about base cost. I'm not even talking about these additional costs, how much less it costs for the architect to do the CAD designs and the specifications for the floors, or how much it costs for the maintenance crew to be able to change something because they don't have to cut concrete anymore. All this leads us to a conclusion that this is not just a cooler way to build, a smarter way to build, a cheaper way to build. It is a greener way to build, because in the end, it considers the full life cycle of the building, and it realizes that the building is not just a pile of bricks. The building is a living, changing entity. From the lower embodied energy of construction to the cleaner installation on the job site to a more efficient operation, we made the building reconfigurable. So now, in 10 years or a year, if you decide that that wall or that floor or that part of the building shouldn't be the way it is, we can change it. We don't need to demolish things. We can make our building reconfigured to the tenant's needs over time. The parts are all reusable and recyclable. It is 95% steel, which means that you can take the components apart, ship them back to us, and we'll recycle them and make new ones and ship them out, and you'll have brand new ones. So they're recyclable, unlike concrete. Concrete, for the most part, goes to waste landfills. And even today's concrete, which is supposed to be lighter and better, it's lighter and better because of the synthetic additives, which make the concrete even less recyclable. You can't even grind it up and reuse it because of all the additives now. It is upgradable now. We come out with new components in a couple of years that make the struts or the joints or the panels better. We buy new panels and people just swap them out. You can make changes to existing space and add in a better floor or better ceiling tiles or better lighting systems or stronger struts. And we're very proud of this. I know this picture is deceptive and people think green building is something that it isn't, but I used this picture on purpose. We literally want to have the living roofs and floors that everybody talks about. And in doing so, we've gone out of our way. I want to jump forward here and show you something. We improved the interior here, not only in the cooler, bigger open spaces with lots of lighting, because with a much lighter floor, you don't need the columns that you had before. But we've actually been working on these panels, which are recessed basins that can handle water and soil. And they have fixtures in them for hooking up to hydroponic systems so that you can water feed and reclaim water from the soil inside or outside your building. So you can essentially have potted plants in the building that are more like a garden than they are like potted plants. And your roof can literally be living roof, but not just be the kind where they just put out some trays. This is literally built into the building with the piping system underneath for it to automatically run it and reclaim the water. And this is the same panel, same space, same standardization as the walking tiles. So you can interchange them. You can use them inside, outside, alongside the existing panels within the same frame. So I actually look forward to the idea of making truly green buildings in this sense here. Go back a little bit though. But from the energy standpoint of green, lifespan is immensely green compared to concrete, which again is in most of tall buildings. In every way, not just in the embodied energy of it, but in the transportation of it, in the waste coming from it, in the better insulation values you get from it, and in the optimization of the building itself. I apologize, here we go. And this is important. The final most green part of it is renovation and expansion, because what's often overlooked in buildings is anytime changes are needed or the building needs to go away, there's very little recycling going on in there. It's pretty much demolition and cutting concrete and waste and mess. And with the safety lifespan system, you can add floors, you can remove floors, expand your building, all just by changing out parts, by swapping out the existing frame, putting part of it to tension, pulling the parts out, putting new parts in, putting it back to tension again. So essentially what you have here is a configurable machine rather than a building. You can resource, reroute everything, all without cutting any concrete, because as far as we're concerned, concrete should not be above the ground floor, except perhaps in columns for load bearing. It's a compressive material. There's no reason to have it in a suspensive mode. As I said, this is really looking to a new way of thinking about buildings, because the old way of building buildings is we have solid stacks of concrete slabs held in the air, poised on top of columns that are, by the way, perpendicular, which is the worst way to hold something, because any kind of lateral shock makes them all just tumble like a house of cards. So you've always got to have bracing and all the things that do that. Whereas in this case, safety span or lifespan is a suspended frame that is actually hung from the vertical members of the building. And what we wind up getting, instead of a pile of building materials, is a dynamic machine. Essentially, they're components within components that hold the entire structure together, become part of the structure, reinforce it rather than put load upon it, and can be configured, adapted, and changed by you. So as developers, we have the ability to construct our machine, if you will, and upgrade it and extend it without having to necessarily pile more building materials on. Now we have something with components that are quantifiable that we can swap out as needed. Overall, the cost for lifespan is roughly comparable on a material level. However, the labor cost for it becomes so much lower once you realize that all the costs of concrete go away and 2 people can install a 480 square foot bay in a couple of hours. So it's really about labor costs and lowering additional engineering costs. In the end, lifespan is actually tremendously cost effective. And in the long term, over the life cycle of the building, I couldn't even begin to calculate the savings I think people are going to get from it, from the use. The real cost of concrete everybody overlooks has to do with all these, they're ancillary, but they're necessary. All the project costs associated with the concrete. So it's not just about concrete and rebar and how much does that cost. It's how much does it cost to lay down a concrete floor? How much does it cost to put the steel in place and lift them in place with cranes and have a crew of 6 guys and have riveting guns to be able to mount down the steel plates with the rivets and make sure everything is cut right, and then cut them with an edge grinder and be able to weld them and do all the things that are necessary to set up for the concrete, and then actually pour the concrete and then wait for the concrete to set. And all that takes days. And because it takes days, the entire project takes months or years. With lifespan, we can literally do the same thing in a matter of hours, because once we have a girder and some holes in it, we can just attach components to it. And once the frame is in place, you can walk on it and use it. That's not even considering the carbon costs of concrete, which not only are the material and embodied energy costs, but as I said, transportation, demolition, the construction itself, the repairs that are done to it, all these things cost carbon and energy, and they all are sending waste material to our landfills and filling up our landfills. 40% of the landfill material is just concrete coming from construction sites being demolished. We want to reroute that. when you look at them side by side, as I said, the price goes down once you calculate in labor. It seems like a lot because you have 96 joints and 432 struts, but you also don't have 360 cubic feet of concrete, 120 pounds a square foot over your head most of the time. When you're standing in a building at any given time, if you're on the ground floor of a 10-story building, it means that every square foot of roof above your head, right? 12,000 square, 120,000 pounds about, oh, no, just 1,200 pounds, 1,200 pounds, right?
Doug, can you hear me?
I can.
I have a quick question. I let you jump past the slide about embodied carbon very quickly. Do you have any calculations about comparing to concrete? And is this recycled steel? I had the impression it was, but maybe it's not.
No, it is recycled steel, and that's part of the point. We try to make our material out of both recycled steel and recycled plastic or high density plastic, like Trex. So,
and I guess I have a question too on the installation. Does it come in, so transporting, it would have to be made at your facility, transported to the site. How does that transport? Does it have to be in grid form when it comes out to the site? You can just assemble it all on site. Okay.
It's always assembled on site. So that's actually the point. You don't ever need cranes to lift this in place. Every component is light enough to be picked up by one person. Nothing in this thing is bigger than or heavier than a human being can handle. So the premise is no one should need heavy equipment, welding stuff, cranes, dump trucks, concrete mixers, pumps, any of that stuff on site, because now your installation becomes a matter of, let me go to the end.
And quickly, can you go back to the slide that you showed the concrete versus the grid?
Sure.
So it looks to me like it takes, not that one, the one that showed the concrete building.
I'm sorry. Yeah.
There.
Yeah.
So the concrete looks to me, and this may just be the visual that you're showing, to have less space floor on each floor than the LifeSpan system because it's three-dimensional.
Right.
Is that accurate or not really?
It is a little bit. You see this drawing here? This is accurate to scale. So what you see on the right is concrete, and we think of it as being thin because it's just it's just 6 or 10 inches of concrete. But underneath the 6 or 10 inches of concrete is 16 inches of steel truss that is necessary to keep the concrete from bowing down. And then you have underneath that the space for the utilities that are usually set aside, and then you have your drop ceiling. So floor to ceiling, we're only about 6 inches deeper.
Okay.
Because if you look at most concrete floors, you pop open the drop ceiling of your floor, you're going to have a foot or two above you before you even see that steel, and then above that steel is another 6 to 12 inches of concrete.
Now, the second point that I think she had brought out was the side to side thing. You don't have as many beams required, so you do get more usable space per floor.
Are you talking to me, or I'm confused?
Just in general, I think she was talking about the other picture that you had.
Yeah. That's not it. It's cool stuff. Hang on. Wow. That.
Oh, this one right here.
Like underneath here, but what you're not seeing here is that you see the way these girders are? The drop ceiling is below those. So really, in fact, when they put the cladding on, this top 2 feet here is actually used by ceiling. That's where your HVAC and your utilities go.
And you mentioned acoustics. I would think steel would carry sound a lot more. Is that something you can completely eliminate with the acoustical tiles and such?
Yes, well, there's 2 aspects to that. The acoustic tiles are a layer, okay? And above that layer then is a fire layer, and then above that is the frame, and then another fire layer, and then floor. So those are actually layers of fabric that are going to stop real sound per se. But as far as vibration is concerned, the steel does vibrate, but the steel, this is something that's not obvious here in this demo because we don't tell people about it, but the struts are such that when they connect to each other, there is a rubberized connection that absorbs shock and it absorbs vibration. So that at any given strut is exactly 30 inches long, right? But it can contract to as much as 29 inches long because of that rubber core. So that if shock comes through the building, like an earthquake, the earthquake can pass through all the components without shattering everything or breaking steel. They all give a little bit and then allow vibration through. The soft effect, though, is because that rubber is there, vibrations from one part of the frame don't transmit to the other. It's effectively like a memory foam mattress, where you can stand on one side and jump, and the wine on the other side doesn't spill. It's like that, because the frame is designed to absorb the vibration between each component as well as between the layers.
Hey, Doug.
Yes.
What's the maximum span on these? You were talking about potentially limiting the number of girders, or?
Yes. We've actually had a lot of engineering looking at that, and this is going to sound, this is where it almost sounds too good. We can go 36 feet with 120 pounds per square foot live load. That means you can almost double the distance between columns and buildings now safely.
And then kind of going back to the embodied carbon, are you guys going to do any cradle to gate analysis, any EPDs or LCAs in the future?
Yeah, we'd like to. We're trying to find a building partner that would be able to help us get real numbers like that. But right now, it's only kind of speculation based on our estimates. We need to kind of get some real field data, which is kind of our next steps. Yeah.
But Doug, do you have some estimates of concrete, at least as it replacing concrete? I think like your website had some claims. I'm just wondering if there are any calculations under that.
Well, my understanding, correct me if I'm wrong here, but my understanding is that roughly every pound of concrete poured is 1 pound of carbon released. So the math's actually pretty linear. If we look at, for example, I'm going to zip down here because we want to talk about comparisons. Here's the South Station Tower in Boston going up. And that building is going to have 51 floors, and it's going to release 52,000 tons of carbon, because by my math over here, they're talking about pouring 70 to 100 million pounds of concrete. Okay. With the LifeSpan system, that exact same building would not release 48,000 tons of carbon. Now, it's not a question of how much you'd use, because I can't do the estimates on how much more efficient the building will be as far as insulation or anything like that. That's the thing we'd have to be able to prove. I know for a fact that just removing the concrete alone removes 48,000 tons of carbon from that building's construction. Every building, right here at WPI, there is a new building going up, and it is 4 stories high, but it has heavy duty floors that are designed to hold heavy machinery. As a result, it has 6 million pounds of concrete inside of it right now. That's 6 million pounds of carbon that were released because that building, that 4-story building, had to go up. We literally could have eliminated all of that concrete carbon. Yes, steel has some embodied energy, but I think, and this is kind of critical here, we're the same, almost the same steel being used in LifeSpan as they're using in, okay, I'm not seeing here. I have another picture someplace, but I don't want to go get it right now. I'm sorry, it's going to seem awkward. But there is just about as much steel in this frame as there is underneath this concrete. Does that make sense?
So you're saying the combination of the rebar as well as
right. Exactly. All this stuff here that they're putting down, this steel plate here, this corrugated steel plate here, as well as these trusses right here, and this rebar that they fill in here, is about as much steel as we use in our frame here. So it's the same almost embodied energy as just the steel they use. Then they pour concrete on top of it. And it's literally unnecessary It adds weight to the thing. It creates it. In fact, they have to calculate the amount that this is going to sag from the weight of the concrete so that they get an even pour on the top, and it actually is like a lens, as you know, because it's so heavy. So when you get a large span like that, in fact, if you go more than 20 feet, you're going to have to get this truss deeper because it's going to have to handle the length of that concrete that you're pouring. So they use more steel, almost, or a little less than we do, but we use about the same steel. And then we have a little plastic for insulation and fire protection. And then we just provide a floor without having to pour the concrete on top. It's a totally usable subfloor that you can put nails and screws into, ready to walk on.
Can you speak a little to the panels themselves and what sort of materials those are?
Yes, as I said, they're sort of like, we've had a couple of options, and frankly, as I said, this is a project here where we're trying to get this to the point of production. We've done the research here in the labs. This is a WPI kind of project, and what we've come up with is Trex for starters, but with a fire stopping back side. So essentially the surface inside is sort of a recycled polyethylene, high density polyethylene that can take a screw or a nail or a tack or glue, and it's got a sort of a roughened surface, but on the underside it has a silver reflective fire stopping panel. And those mount at the joints to the frame itself. You know what, let me jump around here because I apologize. I'm going to jump around here and it'll probably be easier for all of you than watching me do that. As you can see here on the
Did
top.
that answer your question?
Yes.
What's that?
Did that answer your question?
I think so. I mean, I'm just curious how you're getting up to the 8-hour fire rating or 4-hour fire rating.
Oh, well, we have multiple layers of it. So these are fire rated by themselves, and then there's another fire panel specifically that goes underneath these, and then above the ceiling tiles. So essentially, we sandwich the frame in airtight 2-hour fire panels, and there's 2 layers of it.
Okay.
And that also helps not just to stop the fire from spreading, but to keep it contained within the frame. So since most fires tend to be utility fires, if the utility fire happens within the frame, it'll get smothered because both sides of the frame will have the insulating tiles keeping the airflow. That's the plan. And in fact, the same tiles, since it's all geodesic, these same tiles that you would use to build, say, the surface, can be put on the inside of the frame to be able to make HVAC ducts and fire domains.
Okay.
It's sort of the idea here is to simplify this so that facilities can do their own design, HVAC, fire safety, whatever, without having to have a special group come in to do it.
Right. Can these span systems integrate with wood frame construction at all, or are they mostly for steel frame? Yeah.
No, actually, you could technically put them anywhere. In fact, the key here is if you notice this mount point here at the steel, we can just make mount points for wood, for concrete. We have ones that are like pitons that go into stone or concrete, ones that can go on as a belt to go around an existing column without having to damage the column. You can just put a tension belt around it with multiple mount points. One of the whole hallmarks of the system is to be as flexible as possible. And that's why we were trying to make it in such a way that you could use this for almost any kind of architecture, and people can now use this to make their own homes or retrofit existing buildings. For that matter, hollow out an old building and take out the old floors, but use the existing brick walls and put in nice new floors.
And it does aid with the lateral loads per floor, like you wouldn't need any additional moment frames or anything.
No, in fact, you'd use fewer because you're putting less dead load on the frame. So whatever was there before, this is going to probably be lighter then. And there's no reason why this couldn't be used fully 3-dimensionally to make vertical walls as well, or columns. So while this is a tension structure, there's no reason why it can't be used as a vertical column and then filled with concrete, and then the mount points are at the correct geometry for the floor above. In fact, that was an original idea of this, but we've boiled it down to just the floors now because it's critical. but because we see this as a very low-hanging fruit to be able to fix a problem in buildings that has been long overlooked. But in the end, what we're talking about here is a building system that could be used to make columns, walls, floors, anything.
Doug, in terms of training for labor, is this something you would, is it specialized enough? I mean, the way you described it, it sounds like it's fairly easy, that like a GC could learn it fairly easy.
Exactly. In fact, if I could put this up here, that's one of the things that the feedback I've gotten. I've talked to iron workers, architects, builders, developers, and one of the things they all like about it is that it's so simple to use, it's almost impossible to put together wrong. It's like, it literally is like industrial grade Legos that lock together once they're together. And the geometry is such that it's symmetrical and regular. So it's all 60-degree angles and it's all symmetrical. So you're just putting them in and locking a joint to a strut and then a strut to a joint and then a joint to a strut. And that makes a frame. And then you just take the panels and drop them down on the top.
Go to the next slide, Doug.
Oh, sorry. Oh, right, there I am. I apologize, yeah. That was me putting it together in the shop, and it was actually incredibly simple to do. And this was even a prototype that had screws, and the final version has no screws. They just lock together. So it's even easier than this. So you see, the point here was to not only make the building safer, but to make the construction site safer. So if we can remove the welding and the cutting and the concrete pouring and the cranes and all that other stuff, and the concrete itself, which is a caustic material, we can remove all this stuff from the construction site and just make it an assembly type of job. Not only is it easier and safer to do, but it's cheaper to do because I can do it faster. I can put a whole frame together in a couple of hours by myself.
Not only that, but just the, if you were looking at a standardized, like, you know, a 24 by 24 or a 480 square foot one that you were talking about, the actual, just the weight and the heft of the materials to build out and frame the structure is something that could conceivably, people could just do in the back of their pickup truck, and they could carry it by hand onto the site and assemble as they go and build the whole frame out, and with never a worry, it's never going to plug in the wrong place. And you know, if you're going, oops, we did that wrong, you undo it and do it again the way it was supposed to be.
Right. And when you're done with it, let's say you build something, let's say you drove a big old pickup truck out someplace and built yourself a cabin and you stayed there for 6 months, and then you can take it apart, put it back in the pickup truck and go. So you have a portable and deployable building as well, because it's so easy to build that you can take things apart and put them back together again someplace else. That means that the whole building is recyclable, reusable, and reconfigurable. That was the.
And because you can build on top of anything or attach to anything, Doug and I had actually talked, and I said, well, so you could like build a tree house with this, and he's like, oh yeah. So you could have a tree house with 30-foot spans going around the sides.
Right. You don't technically need a foundation, because here's the thing. Like I said, if you build an old building like a pile of building materials, then you need a foundation, because you need something flat and stable to hold your building materials on. But if you build your building like a machine that is self-righting and is itself strong and has integrity, it doesn't need a strong foundation to stay right. It can actually be a self-righting thing, and it's light enough that it can actually, its own forces overwhelm the weight of the building. So you can put it on a fairly stable ground without necessarily having a 6-foot deep foundation to hold the weight of the building. The building itself is light enough that it can sit on there almost like a fabric structure or lightweight wood structure. It itself is strong enough to hold its own geometry.
Doug, you had mentioned that 1-inch kind of flex that it has.
Mm-hmm.
Is that also, could that also be considered like a built-in tolerance? Because we know that construction sites don't come with imperfections, we'll say.
Right.
So does that allow for a certain degree of tolerances for leveling or getting a
no, not that does. That doesn't. There are adjustable ones at the perimeter, though. So the point is, there are interface components at the perimeter where it connects to the building, the mount points where it connects to the building. Those are adjustable for any tolerances. So if this beam isn't exactly where it should be, that's okay. We'll adjust to the 4 inches or 2 inches or whatever it is to the beam. And those are actually adjustable within 6-inch tolerances. So they're really very adjustable, and they're designed to apply and remove tension from the frame if you need to as well. Having said that, The frame itself, all the components have that little bit of give, but it's a nonlinear, very hard give, so that by human standards, you'd be hard pressed to see that inch at all. But if an earthquake hit, each one's going to give before it bends. You get what I'm saying? So
Yep.
That is true, but really that's more like the internal rigidity of your memory foam mattress. If you took any given part of it, it's resilient, but as a whole, it's all seems very rigid because as a whole, they're all holding each other together. So in such a way, in fact, that if part of it were to fail, it would stay straight to itself and sag like a mattress. And it would actually still stay fairly right to itself, but sag like a fabric that had lost connection at one side. So the whole thing is actually designed to be internally self-righting, regardless of the edges, but you can adjust the edges for tension because that's actually the point where you're bearing load and carrying it off to the rest of the building.
Do those edges have thermal brakes included with them? Like say you're tying into a steel frame. We do a lot of passive house work, and I know a lot of people that were interested in this do a lot of passive house work, and we're always looking at ways to get thermal breaks through the shell, basically. Especially when you're dealing with podium buildings, it can get really tricky. So are those integrated at all into this? Like,
not directly, no. Those are just steel mount points. In so far, at least, they're steel mount points going to the centroid of the girder.
Right.
Or to wherever it is on the building system. But there's no concern about heat or anything like that. The whole system, in fact, is just designed to be as open as possible. So nothing's really designed to stop or allow flow of anything. It's all designed to allow flow, essentially, if that makes sense. Except for fire. Designed to stop fire.
And Doug, forgive my ignorance, but you mentioned in terms of building types that this might replace the floor. Obviously, the South Station example, so a high rise, the different floors.
Mm-hmm.
At what size building do people start putting in concrete floors?
Let me get a couple of pictures here.
Like, would multifamily pass a certain?
Yeah.
I don't really know myself, so.
well, that's why I was asking about podium buildings.
I've seen two-story steel structures around here with concrete floors, and I see them going up all over the place. They're on general anywhere from 4 to 6 or 8 stories. There are the big ones. I'm trying to find the one here of the one at W.
But so like a 6-story multifamily, would they have concrete floors or?
They could, but more commonly, here's the problem, and I almost see this as a bad thing, is that nowadays they're making them all out of wood, and wood's great and all, but it just seems so limiting, short-term, and fire unsafe. Maybe I'm just reading into that, or
well, the 5/1 or the 6/1 podium buildings, they would have, traditionally they would have a concrete deck in between the ground floor commercial and the residential above. And that's usually where it transfers the wood frame.
But you're talking about that thermal break issue with the steel.
Yeah, I mean, that's something that is always a concern, especially if you have parking underneath or if there's a parking deck involved. I mean, the passive house principles, yeah, we're looking a lot at how to get that thermal break. And if this had an integrated thermal break within the system, I think it would make it even more viable.
Easier. Right. Do you understand, Doug, what we're talking about?
When a thermal break? Maybe I'm not. Are you talking about just a barrier between the frame and the vertical, the horizontal members, or what?
Well, just for conductive heat loss through the assembly. So you wouldn't have any heat loss going out through the floor plate system to the walls or whatever.
There's no reason we couldn't have an insulating plate in there. They're just now mechanically connected, but there's no reason why they couldn't be. No. In fact, like I said, the layers have been designed specifically to be in, I did this, structural, architectural, and fire protecting, but really what I meant was insulating. So insulating is everything, including sound. and temperature. So these panels here, these white panels here, are a high density plastic that isolates the full floor panels above from the steel of the frame. There's a joint inside there, a mechanical joint that is steel. So those are mechanically isolating the floor from the steel of the frame. We could absolutely put the same kind of thing in between the girder and the joint, the mount point. You understand what I'm saying? So that thermal barrier could easily be put in there. We just hadn't really thought of that, but there's no reason it couldn't be, sure. That's the kind of feedback I want, yeah. I didn't even know that was an issue.
So I think what Travis is saying, so there's a big movement in Massachusetts towards passive house multifamily. And a decent number of those are going to be podium style. So they've got commercial or parking on the first floor. And they're going to have what Travis is saying is that traditionally you would put a concrete deck between that first floor and that second floor.
Right.
And that this could be a replacement for that. But because they're working as a passive house and they're very concerned about thermal bridging of heat from inside to outside the envelope, because that's one of the biggest things that you try and reduce in passive house, is that, so if you pitch this, even, you design one of those white things to break that thermal, that's a marketing thing for that particular style of building. Excellent. And there definitely are a number of those. So Riverside in Newton is, I think, 7 buildings, and actually Michelle knows very well the, I think like Suffolk Down has a number that are likely to go in, and then Northland, which is, I'm forgetting how many buildings Michelle knows, but
15.
15, but not all of those would be podium, right? Like, so maybe
many of them, but
yeah,
most of them, but not all.
Well, anything that's got a concrete floor at all would benefit from this.
And where is this? So you said the engineering testing's been done, but there's still a few things you need on certification to start production?
Yeah, here's our problem. We've done the testing to the degree we can, but in order to build any building, no, that's not true. You can build any building you want. No one's allowed to live in it, and you won't get insurance on it unless Factory Mutual has taken your product and destroyed it 10 times. So essentially, what we haven't gotten to is the official, here's enough of the material to give to Factory Mutual and the $100,000 or whatever it is going to be. We've done the math for the 28 ASTM tests that they need to do to sign off on it to say, yes, you can now build a building in it that people can use. So I could build a demo building with it tomorrow, but nobody could live in it legally and they wouldn't get insurance on it, wouldn't be occupiable.
And how long does that process take? And then I assume you need investment to scale up production as well.
Yes and no. Actually, you'd be surprised. Production itself, we will scale up production, and that won't cost as much as you'd think because it's such a simple design that, as I was telling Jason last week, if somebody told me tomorrow they needed to build a building in October, I could have a friend of mine, or not just a friend of mine, but any one of a dozen different places that do this, manufacturing this next week, because it's
and not only that, but
I'm sorry.
That goes to the transportation costs and stuff. Yeah. I think that was brought up before of saying, well, you'd make them in Boston and have to ship them to California. No, you'd be able to work with a fab shop in California that was local to them and simply send them the CAD things and give them a parts list and a build list and let them rip. And they could, they're all relatively simplistic components to put together that any shop could do it, anyone could assemble it, and from a QA perspective, it's easy to test them, and they would deliver them locally from locally sourced recycled steel or whatever else to the local building location. So you wouldn't need cross-country shipments of things going back and forth.
Right. We're trying to make these as green as possible at every level. Actually make them life cycle products.
And not only that, but there is the economical impact of it is if a building system like this, when a building system like this takes off, you're actually enabling a whole bunch of fab shops to pop up to be able to crank things like this out.
Right. So yeah, well, in short though, what we're looking for is somebody to, or some way for us to be able to get this through Factory Mutual. And that may or may not require building or involve building a proof of concept demonstration building that we can't technically live in or rent or anything, but we use to prove the point. Or it may just be going directly to Factory Mutual. But right now we're at the, I'm sorry?
Slide 29.
Slide 20. Oh, right, of course, I'm sorry. Yeah, I even have my slides up. So yeah, so essentially we're talking about going through our ASTM testing for fire safety, because they have to take enough of our material to build a small building out of, and then shake it until it falls apart and put weights on it and light a fire under it and all that other stuff. So that is actually our ultimate goal, of course, before we can release this. And then after that, yeah, no, we'd probably take 6 months. ASTM testing is supposed to be about, based on the 28 tests, I'd say about a year's worth of testing at most. Probably 6 months to a year, more dependent upon their backlog if they have any, but I don't know that they do. And then in the meantime, our other, we were also looking at the possibility, like I said, of building a proof of concept building here at WPI or nearby, just to be able to use it as a proof of concept and to test it and demonstrate the wearability and the usability and make sure that we get the same results out in the real world as we did out in the lab.
So I know Michelle and Travis, oh, go ahead, Michelle, go.
I was just going to comment back on the embodied carbon conversation for a minute. I was just thinking that, like you were saying, Bev, it could be, I think it could be really compelling if you can sort of attempt to quantify it in some way, because I think it will tell a really good story. And like Bev said, that's really sort of taking off, at least in our area. And, you know, some municipalities are even starting to consider requiring embodied carbon analysis for projects. And I think I was just going to suggest that I think that a relatively straightforward process could be using Tally for Revit. And I actually think this could be potentially a perfect research project for like a graduate student in engineering or architecture, to build, you know, the exact same building, simple, you know, rectangular 4-story building or something, with typical, you know, concrete slab construction, and then build the same exact building with your system. And then Tally, you would have to, so Tally, it would be relatively easy to assign materials to the concrete building. And then in the LifeSpan building, you would just have to assign steel to like each of the components. You know, it would be a little bit more, you know, complicated, but again, I think a student could probably take it on. And you could actually just do an analysis and it would spit out like the embodied carbon comparison of the two assemblies. And I feel like that could be some really compelling information.
Yeah, I totally agree. You can also use the EC3 tool, which is a free online tool. It's in beta testing, but it's another embodied carbon tool for buildings.
EC3?
Do you think you could, I was thinking about that, can you pull apart the components though using EC3?
Not as much. I mean, you can, one thing that they rely on a lot are the EPDs, the environmental product declarations,
Right.
or the LCAs. But if you went through an EPD or an LCA analysis and got in those databases, it would actually kind of streamline your product into like declare product valuations, or, you know, there's different certification bodies you kind of get tapped into when you do an EPD or an LCA analysis. And there's a number of third-party consultants that will do those for you, and to varying degrees of expense. And I think those take about almost the same amount of time as the ASTM. It's about a 3, maybe a little less, 3 to 6 month process to get those done.
Yeah, and the benefit of EC3 is that it's free,
Right.
whereas Tally is not. But
Right.
yeah, I think it would be interesting to use one of those to try to assign, you know, the materials to all the components and get sort of as close of a comparison as you can.
Yeah, I mean, I was
Because
kind of,
I wonder a little bit about just, you know, making sure like the plastic components are in there and sort of everything in the sandwich is, you know, comparable to the the concrete slab and just see where it shakes out. I mean, it sure seems like it's going to be a significant reduction, just getting rid of all the concrete.
Right. Yeah, and that's why I was asking about the floor panels too, because you could roll that into part of the analysis. Like if you had, if you have different sandwiches for different assemblies, you have your 2-hour rated assembly, your 4-hour rated assembly, or whatever, or a Cusco assembly. Each of those could have their own product declaration too, associated with embodied carbon. I mean, it's a lot, but at least it would give everybody a good understanding, when they have the kit of parts, essentially, or the hydroponic panel,
Right. So, okay. So if you could send me the links to some of these things, Leslie.
Sure.
Yeah.
We're getting notes here. I just don't know if these sound like tools that you guys are already familiar with.
Yeah, I've
Well,
been
I
typing furiously.
Michelle's idea of getting a graduate student to
Yeah, I like
try
that.
and analyze. You know about our internship program, right?
No, I just know
So
about
we
WPI.
pay for college students to come work for you for the fall, half-time. So if you know of a person that is good, we can get you in. There's only 50 spots left for the fall is the thing. They're going very quickly. But
Okay.
if you know a WPI student that would be able or interested, so an architectural or structural or somebody with obviously some quant skills you would want to hire, reach out to us but we would need to move very quickly on that.
Okay, that's very good to know. Thank you.
And if it didn't work out this semester, we could work it out in the spring. It's just, pairing sometimes takes longer than you think, but we could get you all set up for the spring. And so an environmental product declaration, I think, is a good thing to think about, as well as the, what did you call it? The testing, the safety testing that you need to go through.
Oh, the ASTM testing.
Yeah.
The ASTM is really just for a product. It's like UL testing.
Right,
Yeah.
right. And then I guess I'd really like to also either send this presentation or have a follow-up conversation with some people with a little more structural engineering background, because I think Michelle and Travis and I and even Leslie, we know certain things and we know how this could be appealing, but we don't necessarily know have the chops to understand how much could be replaced and in what places and where it wouldn't, right?
Yeah, no, I agree completely. Just so you know, I'm surrounded by mechanical and structural and civil engineers here at WPI. And when I talk to people over in the civil engineering department, first of all, I was happy because I went into one of them to talk to him, and he had a model on his desk of essentially the collapse of a building that I'm trying to replace. So his focus is stopping buildings from collapsing as well. And after we talked about this, they're not only sure that this is really the cause of most collapses, but and this is important here, if you look at the screen, it's the only reason why we can't build taller, bigger buildings, because we've literally hit the growth limit with concrete, because by the time you get to a certain height of about half a mile or so, you start to have to really reinforce, as you know, the bottom of the building, because it's like a tree and you need it to get thicker as you get taller or stronger, because it needs to hold up all its own weight. Well, by lowering the weight of each floor, we could allow them to make safer, taller buildings than they can't make now. And that's what every architect I looked at it said, well, now you lifted the ceiling on making tall buildings. You could literally make, this image here is Frank Lloyd Wright's Mile High Tower in Wichita that he wanted to build. You couldn't build that now. You can with LifeSpan. And that's what most of the architects I talked to said. So if you know structural people, please show this to them. I have a feeling they'll probably do the same thing. So.
And I guess there's also an organization called, and Michelle, you probably know it better than I do, Structural Engineering 2050. So it's a bunch of structural engineers that are worried about the embodied carbon of what they're specifying. I mean, I'd like to engage some of those people. I tried to reach out to some of them. I think it's just hard to attract people's attention this time of year, honestly, and with COVID. So
COVID.
Yeah.
Okay.
And Doug,
Yeah,
for
no,
posterity,
I think,
since
actually,
this is
Bev, I
being,
think next week's, sorry.
Nope, go ahead.
Next week's Embodied Carbon 101 for BSA.
Is I believe they're doing a deep dive into SE 2050. I'm fairly certain that
Oh,
there was like an
really?
intro this past Monday, and I think next week, I'm pretty sure Mike from LeMessurier is presenting on the Structural Engineering 2050 Challenge and getting into the deep dive of how they are quantifying the embodied carbon of structural systems. I'm pretty sure. So it's on the Boston Society of Architects website.
Mhm.
And there's a whole series of these, and I think that is next Monday.
Yeah, and you can buy just one session and it's not that expensive. So
Right.
I would recommend, Doug, that you listen in on it just so you know the players and sort of the perspective. But those are the people you really want to get to.
Okay.
Yeah, there's also the Carbon Leadership Forum.
Yes.
I just saw something recently. I think they have a webinar coming up with structural engineers through that forum as well. Might be worth taking a look at.
All right. Thank you very much. I might have missed some slides here, but like I said, this is more of a conversation. So how do you feel?
Great. Well, I apologize, Doug. I need to get going. I'm late for something else, but it's great that we recorded this. Leslie and I can cut out the beginning of it and forward it to the other people who weren't able to make it, and maybe try and collect comments, and then we can talk about next steps. So.
Excellent.
Any and all feedback is welcome.
Yes, thank you. Yeah, always. Like I said,
Thank you, Michelle and Travis, for joining, and sorry about the snafu and that this went over. So.
Yes,
No problem.
No problem. Thanks. It was great. Really interesting.
Thanks, everyone.
Thank you.
Take care.